Hello, students. Today we're going to simulate what I believe is one of the most exciting and scientifically important papers that has ever been published. It's the work of Robert Millikan, his oil drop experiment, where he was able to measure the fundamental charge, the charge of an electron, using oil droplets. And what he did was he was able to measure the charge on a multitude of oil droplets and put them in his device, and then he could measure the electrical charge that each oil droplet had on it. And he reasoned that if he took a large collection of those charges and looked at the smallest difference between two charges, that would have to correspond to one electron's charge. And the experiment worked beautifully. It was similar to some experiments that had been tried on water and some other things earlier, but water and the other liquids used evaporate over time. And so the mass of the droplet kept changing. Well, with oil, it has a very low vapor pressure, so Millikan was very smart to choose oil as his medium and to do the experiment based on oil drops. This paper is referenced at the top of the page here. It's by Robert Millikan in Physical Reviews way back in 1911. But it is one of the most exciting papers I've ever read. The language is not as stilted as we use today, and you could just feel the excitement that Millikan had when he was moving those oil droplets up and down inside of his apparatus and measuring the charge on them. So it's a very, very good, interesting paper. And if you're interested in the history of science, it would be a good paper to look up and read for yourself. What I'm showing you today is a variation of an experiment that I published in the Journal of Chemical Education in 2006. It was to use magnetic strips, refrigerator magnets, cut into little pieces to resemble oil drops, and BBs to represent the electrons. And the experiment was similar to what Millikan did, in that what we did was we would put these oil droplets, refrigerator magnets, into a dish of BBs and let all the BBs just collect on those refrigerator magnets. And then we would take each oil droplet out and strip off the BBs, not counting them, but just strip them off and weigh them. And then we would get another oil drop, strip off the BBs, and weigh them. My assumption, like Millikan's, was that the smallest difference would represent the mass of one BB. So we were able to measure the mass of a BB without ever weighing any known number of BBs. And that's exactly the way Millikan did his experiment. Now, I'm also working on another publication that is designed for situations like we're in now. The first paper, based on mass, depended on having a good balance, about a 0.01 or better gram balance, in order to do the experiment. Most of you would not have that sitting around on a shelf at home. So what I've done is I have modified the experiment to determine, instead of the mass of a bead, we're going to determine the diameter of a bead. And we're going to do that in the same way. We'll get the diameter of several magnetic beads, and then we'll measure the length of that string of beads, and then we'll rank them. So let's go through the experiment, and I'll show you. Here I have some oil droplets. They're different sizes, and you can see these are neodymium magnets, so they're extremely strong magnets. And when you break off a little piece of them and put them together, they'll form circles just like this. So these are our oil droplets that we're going to use in this experiment. And what we're going to do is to take each one and measure the length of it. The procedure is on the Excel spreadsheet, and we'll be following it line for line. So let's do the first one now. This is my first BB, or in this case, magnets. And you see when you pull them apart, they do stretch out into a straight line. So we're going to lay them here, and I'm going to line them up on this figure. And when I do that, I'm using the 10 instead of the 0 mark on the ruler. It makes them easier to get an accurate measurement. So this is it goes from 10 to 14.5. So this is going to be 4.5 centimeters long. So let's now go back and record that datum. And the first one was 4.5 centimeters long. Okay. So now let's go back and get the next oil droplet. So we'll do that. We'll put this one back together. You see how they snap together like that? And so there's number one. And for number two, we'll take it apart and it straightens out into a good straight line. Let's measure its length. And for this one, I wish my camera had enough resolution that you could measure these yourself, but it doesn't. So this one I'm having a little trouble getting it to stay straight. Okay, now I got it. And it's exactly 15, from 10 from 15. That's going to be 5 centimeters in length. So let's go record that datum as well. And we've got 5 centimeters. And now let's go get the next one and put this one back. So let's snap him back together, put him here where we started. And we'll get this one. We open it out. There we go. And now this is number 3. And let's line it up and measure it. Okay, that would be about there. And this is 15.5, so that would be 5.5 centimeters in length. So let's enter this value. So this one is at 5.5 centimeters in length. Now we'll go get the next one and close this one back up. And we'll get number 4. And we open it out. And we'll try to lay it good, nice and smooth, flat against the ruler. And it is at 18.5, so that will be 8.5 centimeters in length. Record it. And this one is at 8.5 centimeters in length. Let's put that one away and get the next one. And we'll put it here. Get number 5. Number 5, we'll open it out. And this is 14.5, 10 minus 14.5, that would leave us 4.5 for this reading as well. So let's record it. And this one is at 4.5 centimeters. Okay. And we can now make the next reading. Got half of our values. And we'll do that. Oops. Now that was what I was telling you about. These things are very powerful magnets. So Oh, well, as you can see, I'm having all kinds of trouble trying to get this guy back together. And I'm not really sure. Let's see if I got the right number of BBs magnets back on. What did we read? The last one was 4.5. Okay, yeah, I did. Okay, now let's go back, go get the next value will be for number 6. If we open it out, and we can measure the length of the line of magnets, that's exactly 17.0, so 10 from that would leave 7 centimeters long. So let's record number 7. It's number 6, I'm sorry. It's 7 centimeters long. Okay, now let's go back. Put number, no, that was number 6. Yeah, it was. Yeah, that's right. Okay, and now we get number 7. And let's see how long it is. Number 7 is exactly 6 centimeters long. So this one's 6 centimeters. So go here. And number 7 is 6 centimeters long. So then we'll put it back together. Get number 8. All right. And let's measure number 8. That looks like it's going to be exactly, yeah, 15. So that's 5 centimeters long. So I'll go ahead and record it here. And then we'll go back and I'll show you where I did the measurement. See, here it is there. So it's 5 centimeters long. Let's put it back together. We've already recorded the data on that one. Let's get number 9. And we open out number 9 and let's read it. Number 9 is 4.5 centimeters long. So let's go and record number 9. 4.5. Okay. And number 10. Let's do number 10. I just put number 9 away. Number 10 is a lot longer, and we're going to use this as a test to be sure we got it. We did do everything correctly. We'll include it in the data, and then we'll see. Okay, it goes from 10 to 22, so that would be 12 centimeters long for this one. So this one is going to be 12 centimeters long. Now I'm going to include 0 because a line of 0 length would have 0 for the length. So what I've done now is I have all of our data collected. I'll leave the last one on, so once we're done, we'll determine to see if we got it right. So now, what we're going to do is to take the data that's in here. I'm going to multiply it first by 10, so I get it in millimeters. I'd like to use millimeters instead of centimeters because BBs certainly are much smaller than a centimeter. So let's do that. And what I'm going to do is I'm just going to multiply the values we got in the first column by 10. So this value is equal to this one times 10. Okay, so it's 45 millimeters. And then we're going to do the same thing for all the rest of them in the column. So I'll copy that cell, and it copies the formula and then does the same thing that the first one did. That's the way Excel works. It's a very good spreadsheet. And part of this experiment really is to get you familiar with the things you can do with Excel. Okay, so now what I want to do is take each one of these values now and sort this. So I'm going to sort the data that I have at this point. So, and I go up to the data. Oh, I'm sorry. I should have been sharing this all with you. Okay, so let's get back up there. Okay, so what I've done is I've taken this value and I've multiplied it by 10 and put it here. Then I took this value, multiplied it by 10 and put it here. This gives me now data in millimeters of millimeters. And I'd prefer to use millimeters. Now I'm going to sort it. And the way we sort data is we highlight it like I've done here. And then we go up to the data column up at the top, and we sort it, and we're going to sort it. I didn't highlight the headers. I want to do that. Okay, so now I want to go sort this, and my data does have a heading, and it's right now looking at sample numbers. What I want to do is look at the sorted column, which is going to be this one, and I want to sort that from largest to smallest. Okay, when I do that, now you see the numbers have all been rearranged, but now these data are all in numerical order. The 120 was the number 10 set of magnets, and it goes all the way down as we go through here. Now, what I want to do is go over here, and I want to get the difference between each one of these and the one just above it. And then we're going to look at that. So what I'm going to do is I'm going to have Excel subtract this one from this one. So it's going to be equal to this value minus this value. And that'll give me the difference. Now I want to subtract, I want to go down and copy that same formula, do each one of the subtractions all the way to the bottom. All right, so here you go. Now, when we get a 0, that occurs because these two numbers were exactly the same size. So I don't want to include the zeros in my measurements. And I want to look and see the other values that I've got. And not counting the zeros, 5 is the smallest number that I have. So the average in this one is 50. I'm sorry, 5. And so that represents the smallest value that we've got. Now, I'm going to copy all these unique differences over here so I can see from here down to here, I've got the same number. So I want to do a copy. But when I paste this time now, I just want to do values, because if I kept doing that with formulas, then the numbers would come out all wrong. So I just want to copy the values over here, not the formulas that was used to calculate them. This is another value of 5. I've got another value here of 5, so I'm just going to copy it in here. And so that was this one. And I've got another value down here of 45. Okay, so now I've copied over here all of the unique differences, and you can see that the smallest value is exactly 5. So the average of all those 3 values there is 5. So that's the smallest number for the value of the number of BBs, or in this case, magnets. So now I want to go back over here and calculate the number of magnets, it should say instead of BBs here. I'm going to calculate the number of magnets by taking this value for the length and dividing by the value of each one. So this value is going to be equal to this number in this cell divided by this number. Now, since I'm going to copy this same procedure all the way down and subtract them all, I want to subtract all of them from this value. Now, Excel, if I just push this sign, everything would come out right for this column. But when I went to the next column, what it would do is take this number and subtract from the one below it, and then this number and subtract from the one below it. We don't want that to happen. We want to lock this cell in, and the way you do that in Excel is you insert a $ before the G, which means do not change column G, and we put a $sign in front of the 34, telling it no, do not change the value in row 34. So now when I do the equals, it says there would be 24 BBs in this top one. And so let's just keep on going down below. Let's go copy that cell and put the result in this column. Okay, so it does turn out that these already came out to be whole numbers, but in other experiments they wouldn't. In the mass experiment, there would be some variation, at least in the second decimal place in the masses. These all came out to be whole numbers, but what we want to do to guarantee that, and you'll need to do this down below when we do the rest of the experiment that I'm going to talk about in a minute. What we have to do is round these numbers off. So this value is going to be the round of this number, comma, 0 tells it to keep no decimal places in the round off. And put that in the wrong cell, but it's the same. No, let's undo that. I need to put it right here. So this number equals round of this number round of this number, comma, 0. Now that should be correct. And of course, nothing's going to change down through here because all these numbers are whole numbers. But we're going to go ahead and do it as if they weren't. Okay, now, so we've got our table of data, and I've already set up Excel to do the graphing for you. And on the table, it has the equation for the line. Y is equal to 5x plus b. In this case, the intercept is 0. So it's y. The 5 is the size of the magnet in millimeters. And the r² value is 1, meaning there's a perfect correlation between the length of the BBs as we measured them and the number of magnets that's present. So that's outstanding data, of course, and we expected something like that. Now, it says this first line should be 24 BBs long. So let's go back over and double check and see that it is. So there's 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24. So we've got 24 BBs. That is correct. And I'll leave them right there. You can probably see the resolution and count them for yourself if you think I made a mistake or something. Okay, so it is giving us the correct number of BBs in that line, which means we did get the correct diameter of the BBs, in this case, the magnets. Now, these are precision magnets, and they were supposed to be 0.5 millimeter or 0.5 centimeter, 5 millimeters in diameter. So I know also that that is correct because I ordered those magnets. Now, I want you to follow exactly the same procedure. So let's go up here and look at what we want to do for the Millikan experiment. Now, down below, I've copied the data. It's referenced right here from Millikan. And he had one table that had 37 measurements of charge. I think this one was actually made on the same single oil drop. He just kept moving it up and down and remeasuring it in his apparatus. And the charges are listed in ESU units, but in order not to carry that multiplier, this first value was 34.47 times 10 to the negative 10th ESUs. So what he did is he multiplied every one of his values by 10 to the 10th and just reported that. Because when you multiply 10 to the minus 10 times 10 to the 10th, it becomes 1. So he recorded these as numbers without the multiplier 10 to the minus 10. But you need to remember that each one of these values, this first value and all the ones below it, this one is 34.47 times 10 to the minus 10 ESUs. Now, when you go through the analysis as we did up here, the slope of this line that's going to appear when you put the data in correctly and do what we did before, the slope of that line is going to be the charge of one electron in ESU units. So the slope will go right here. That'll be the mantissa of the number, and the exponent is 10 to the minus 10 ESUs. So once you get this data filled out, this is what you will get then. Now, if we go up to look at what we're supposed to do, once we've got that number, you want to divide your answer in ESUs by 2.998 times 10 to the 9th to convert it to coulombs of charge per electron. Now, you'll need to multiply that by Avogadro's number to get coulombs of charge per mole of electrons. And then I want you to take your textbook. Let's stop the share for a moment. If you take your textbook and look inside the back cover, we can't focus on it on the camera, but there is the elemental charge, 3.602 times 10 to the negative 19th coulombs. That'll be the value that you'll get from the table. So I want you to compare your answer to the table value by getting the percent error that you got. And I want you also to include the R² value as an indicator of the precision of your measurements. It'll indicate how much scatter you get in this set of data. I think you'll be surprised at how good it is. And then report that to me in the Dropbox on D2L before the deadline. So this is a really good experiment, I think. It's really exciting when you realize you have just done a fundamental calculation for the charge of a fundamental particle that was done first time accurately by Millikan in 1911. So I hope you enjoy the experiment, and I hope you will do some reading on Millikan's work and see why I'm so excited about the paper that Millikan published way back then. All right. So that will complete our experiment for today. And I wish you the best and stay safe and healthy.